Yeah, thank you for the introduction, and thank you everyone for coming to my talk. So today I will give some examples on how we can use generative models to solve some of the computational issues in sampling. So actually, before this talk, I was curious to see what people have been talking about at this online seminar, and I saw several talks was on using generative models to do sampling, but I should tell everyone there will be no diffusion models or ordinary differential equations involved in this talk. But instead, I think we offer a nice and elegant approach for a classical sampling question. So given the background of the audience, I will go light on the background. So we focus on parametric models. So the Bayesian framework assumes there's a true parameters behind the data generating process, say p theta n. And after we observe n data points realized from this process, we update our beliefs about what is the potential location of this true parameter. So in the Bayesian sense, this is categorized by the posterior distribution, which is proportional to the product of likelihood function and the prior. So Bayesian inference provides this nice and coherent way to do uncertainty quantification. And as you receive more data points, you can keep update your beliefs using the same framework. But it's no secret, especially here is the seminar on Monte Carlo methods. Sampling from this posterior can be computational challenging for various reasons. And people have proposed all different kinds of computational algorithms to solve these issues. So we will show a slightly different approach here using generative models. And to be more precise, I considered the scenario where you have an easy to sample reference distribution. It can be your prior distribution, a standard Gaussian, or a standard uniform. But the problem is you have a hard to sample posterior distribution. So our goal here is to find a push forward mapping T such that T can push forward the reference distribution to your targeted distribution. So in other words, if I can generate IID samples from the reference distribution, the ZIs, the transformed variables TZIs should be independent draws from my targeted distribution. So the benefit of using the generative models is once I learn such a push forward mapping T, I can generate arbitrary numbers of draws from the target distribution at a very low computational cost. And in this talk, we consider the scenario where the posterior is now up to a normalizing constant. So this is your sampling one-on-one situation. And we will find such a map T using guidance from optimal transport theory. So we consider the classical sampling question. I know the density of the prior, and I have the density for the likelihood function, but I just cannot compute the denominator here, the marginal likelihood. It can be, this is a too complicated integral to compute. And the two of the most common approaches for this type of problem is the first one is MCMC family. So essentially, we want to construct a Markov chain such that its stationary distribution will match the target distribution. And the benefit using MCMC is once your chain has converged, you will get almost exact samples from the target distribution. But we all know that it's very hard to train Markov chain. You can have slow mixing, correlated draws, and for a lot of situations, you actually never know whether your chain has converged or not. So the second type of approach for this type of question is a variational base family. So essentially, we turn this sampling question into an optimization problem. You pre-specify approximation family, and you want to find which distribution in this family is closest to your target distribution. Since it's an optimization program, it's fast and scalable to compute, but you also pay a cost, say using approximation family, or you sacrifice the dependence among the parameters. You won't get exact draws from your target distribution, and this oftentimes can lead to biased estimate or improper uncertainty quantification for your downstream analysis. So as I mentioned earlier, we use a different approach. We want to find a transport map that can push a reference distribution to your target distribution. And for this talk, we wanted more than just a transport map. We specifically require it to be the optimal transport map defined in the Monte problem. So what this means is among all the map that can push mu to pi n, my target distribution, I'm only looking for the one that has the smallest L2 distance between the reference distribution and my targeted distribution, and a transformed distribution. So you might wonder, since my goal is to do sampling, any transform map that can push mu to pi n will achieve this purpose. So why specifically this OT map? So it has both computational advantages and inferential advantages. So first, by looking at only the optimal transform map, we are guaranteed the uniqueness of the solution. So this will usually give you some numerical stability in your actual implementation. And the second, we will show later, this OT map enjoys superior inferential properties, and we refer this as rank-preserving properties. And here is a motivating example on what exactly is this rank-preserving property means. So let's visit a question, say, how you wanted to construct a credible region for a multivariate distribution. So what we usually do is I look at the marginal distribution. Say if I have a bivariate distribution, I look at the marginals. And I draw the 95% credible intervals along each axis. And this will give me a box region that capture a majority of the probability mass. So if you are lucky, your posterior distribution has this convex distribution, or if you're extremely lucky, this posterior distribution can be approximately Gaussian. And then we know for a Gaussian distribution, the optimal credible region should be a circle or ellipsoid. Then when you make the decision based on the box or the circle, usually you won't make very different decisions based on these two regions. But the problem is, what if your posterior distribution has this non-convex distribution? Say, for example, here you can have this banana distribution. I can also look at the marginals, and I draw a box. But this box doesn't tells me any information about this geometric structure of the posterior distribution. So the last plot is what our method is able to do. So here we can generate quantile regions at any levels. Say, for example, here we'll produce credible regions at 20%, 50%, and 90%. So all of the three quantile regions were able to capture this non-convex shape of this banana distribution. And they say you took better care of the correlation among different parameters. And this will give you advantage, say, doing downstream analysis. So here is the outline of the talk. So first, we wanted to answer the most important questions, how you actually find this OT map when you have an unknown normalizing constant. We will have two scenarios. The first one is relatively simpler when your theta is continuous. And then we'll move on to slightly more challenging question, especially for MCMC algorithms. What if you have a multimodal distribution? And we will revisit the examples on how we construct the multivariate quantiles using our OT map. And we will show this is efficient tools to do posterior summaries and exploratory analysis. And the second scenario is slightly more challenging when theta has both continuous and discrete components. And this is really common in Bayesian inference. We use latent variables all the time. And we will show this is a slightly more challenging case to find the OT map. And this is the part where this talk will get really technical. And then we will give some special designs of the transform map to further reduce the computation complexities for specific models. And then we wrap up with some simulation examples. Maybe I want to ask if there are any questions about the background of this talk. Okay, I think everyone is on board. I'll keep going. So finding the OT map requires the map to satisfy two conditions. So the first one, it has to be a transport map that push mu to pi n, push your reference distribution to a target distribution. And this is not a directly invertible object. Here's a question. Is the rank preserved with all cost functions? That's a good question. You have to consider L2 loss to have this property. And we didn't really show that in the talk. It also has a requirement on your reference distribution that it has to be a spherical uniform distribution. So we used a standard Gaussian for this type of applications. So let's go back to how you find the OT map. This is not a directly invertible solvable object. And you have an unknown normalizing constant. And the solution is really easy. I use the variational base loss function. I try to minimize the KL loss between the transformed distribution and my target distribution. And then the normalizing constant will drop out of the optimization program. So the second condition is I require it to be the OT map defined in the Monte problem. So among all this map satisfy condition one, it has to be the map that minimizes the L2 distance between Z to TZ. So the most straightforward solution is why not just add this L2 loss as a regularization term? And this has been done by two researchers from MIT in 2012. But just like any regularization approach, you will introduce a bias term proportional to lambda. And in real implementation, you also usually need a data-driven way to select the lambda. And we wanted to avoid that. So instead, we guarantee the uniqueness of the solution by imposing a structural constraint on this transport class, the pre-specified transport class. And this structural constraint is motivated by the OT theory. So in the proof of Brenner's theorem, it's basically saying that under some mild conditions, the OT map is unique, and the map, a T star, is the OT map if and only if it can push mu to pi n, and it is the gradient function of a convex function. It's the gradient of a convex function. So the reverse is also true. If you can find a convex function such that its gradient function can push mu to pi n, then this gradient function is the OT map. So in the easiest case, when you have a univariate, so you want to push a one-dimensional to a one-dimensional, then this convex gradient of convex can be simplified to be monotonically increasing. And this is why this is only valid if you use the L2 loss. And this is also how why we said the rank preserving property will only be valid if you minimize the L2 loss. So this motivates our choice of the pre-specified transport class. So instead of just looking at any transport maps, I restrict myself to consider all the functions at all the maps that are gradient of convex functions. So based on the theory, there will be only one solution in this class that can push mu to pi n. And this is the OT map. So this will also, so if we are doing optimization within this transport class, this means we also have a unique solution to the KL loss function, to the KL loss minimization program. And the solution will be the OT map. So this is I think it's a very elegant result. So we are considering a constraint optimization program now. And when you have a continuous theta, you have even nicer property. Your OT map will be differentiable and invertible. And the U star, so oftentimes we refer this as the optimal potential function, will be twice differentiable and strongly convex with a positive definite Jacobian matrix. And in this case, you can further refine your T, the pre-specified class, to be the gradient function, the gradient of all functions that has a positive definite Jacobian matrix. So we in our paper, we specify our own choice of such U, and we find it work well enough. And to compute the KL loss function, say essentially we still want to minimize the KL loss function. A difference between our approach and the variational base is we do not directly have an analytical form of the transformed densities. You can do the change of variables, but usually it's very complicated and required to compute the inverse of T. But the benefit here is when the T star and every T in this pre-specified class is invertible, so that's valid when theta is continuous. We can apply the inverse map to both sides of the KL loss, and you can rewrite the original KL loss to be this new loss function, and they're equivalent. And it's much easier to compute every item here in this loss function. So by solving this loss function within a constraint class, you will find the OT map. And then what about the case when theta is continuous but multimodal? This was usually the challenging case for MCMC algorithm, where you struggle to learn all the modes. So the theory suggested that when your target distribution is multimodal, it's more efficient to learn each mode separately. So this lemma from Kitagawa and McCain in 2019 suggested that if the support of your target distribution is a union of well-separated subspaces. So for this example, if my target distribution is, for example, is a mixture of two Gaussians, and these two Gaussians are well separated, it's very hard to learn one continuous map that can push a standard Gaussian to a mixture of two well-separated Gaussians. But based on the geographical location of the two clusters, it makes sense to me that the left-hand side of my reference distribution should be pushed forward to the left cluster. And the right-hand side of my reference distribution should be pushed forward to the right cluster. So what the theory suggested was it's more efficient if you are learning two maps where the T1 is trying to learn how to push a blue to blue. And the T2 is trying to learn how to push red to red. And in this case, the OT map, the optimal transport map in this case is the maximum of the two maps, the maximum of T1 and T2. So motivated by this lemma, we will define our U function as a maximum over K convex spaces. And this maximum is a maximum of convex units. And this maximum function will automatically take care of, say, this assignment problem, which part of the reference distribution should be mapped to which cluster. So if you have idea about how many modes exist for your target distribution, you wanted to set K to be exactly that number. So if you don't know the number, you can always do adaptive search. You can start with a smaller number and gradually increasing the increasing K, and usually over-parameterize the convex spaces will not be harmful. And now we want to revisit our previous example, say how I construct a meaningful credible region for a multivariate distribution. Since we are using the OT map, our method is actually closely related to the center outward ranks and quantiles proposed by Halin et al. In 2021 Annal of Statistics paper. So what we do here is it's very easy. If I choose my reference distribution to be a spherical uniform distribution, say a standard Gaussian, I know how to construct quantile contours. It's just circles whose radius is determined by the quantiles of a chi-square distribution. I can generate draws from the quantile contours of my reference distribution, and I map these draws through my OT map. And this is how I get, say, the 20%, 50%, and 90% quantiles for this my target distribution. And I do the same thing for the directional information. So in the Halin et al. Paper, this is referred as the sine curves. So if I look at the axis of the reference distribution, this axis partition my reference distribution into 4 equal probability mass. So I will expect the transformed axis, the transformed sine curves will give me some directional information. And these sine curves also partition my posterior probabilities into 4 equal probability mass. We also have examples where another type of transport map method, the normalizing flow with a planar transformer. So you can see here for the banana distribution, you can produce posterior samples that's similar to the true distribution. And for the quantiles, you also approximately capture this banana shape, the non-convex banana shapes. But if you look at the sine curves, the directional information is completely distorted because the OT map, the transport map here does not have the nice rank preserving property. And this phenomena is even more obvious in our next example. Say if I consider making quantiles on a mixture of 2 Gaussians, where in the previous example, we should know that you will split the reference distribution into the left side and the right side, and there will be a map to the 2 clusters in this example. And that's how our OT map was able to capture this information. And the transformed sine curves also showed how the probability mass was split, while for normalizing flow in this case, you can see a more obvious distorted directional information. So comparing to other transport map method, our OT-based quantile preserve the geometric structure and also the directional information of the distribution. So this is useful when you have a 2-dimensional, you have a bivariate distribution. You can directly visualize what everything has been going. So when you have a even higher dimensional case, we think this multivariate credible regions offer a convenience framework for you to do, say, exploratory analysis. So we present 2 examples here. The first one is you can use these quantiles to construct 95% simultaneous credible intervals. And actually saw Galen Jones mention this concept a few weeks ago. So essentially, here I wanted to construct coordinate-wise intervals. So I could construct AI BI for every theta I. And these intervals will give me a joint probability that for each coordinate of the theta falls into this interval, the joint probability of these events should be greater than 95%. So this is different from, say, the marginal credible intervals. This is what people usually use to say, if you want to control the family-wise error rate, you want to minimize the chance of you making at least one error. So usually for multivariate thetas, you can either use a Bonferroni type of correction, which will be extremely conservative, or you need to find a way to figure out where is the high density region, and that can also be challenging for high dimensional theta. And I think our approach could be a much simpler solution to this question. So essentially what we do here is we will take draws from the 95% contours of the reference distribution. So we will use standard Gaussian, and essentially the draws will be just uniformly on a ball sphere, which radius is determined by the chi-square distribution, the quantile of chi-square distribution. And then we map the draws from these spherical contours through the estimated OT map. And the theta j here will give us, will categorize the 95% credible region contour. So you can think about it is we map a ball sphere through the OT map. You will still be, say, a banana sphere or an elliptical sphere. It's not it's a hollow inside, and and usually this step is really cheap to compute. And then our third step is to find the smallest box that can contain this 95% credible region. So essentially, you just look at what is the smallest and the maximum, what is the smallest and the biggest values coordinate-wise. And this, because the 95% credible region will guarantee to contain 95% of the probability mass. So this, the smallest box that contains this contour will automatically have at least 95% posterior probability mass. So this simultaneous credible intervals can be a nice way to have an interpretable and a visualizable summary of the joint posterior uncertainty. And the second example we give here is we think it is possible. So using the OT map, you can also quantify the posterior. If I give you a theta null value, say I have this candidate value in mind, I want to see how plausible it is under the posterior distribution. So we think this potentially can be a Bayesian analog of the p-values. So usually the p-value is quantifying the plausibility of the data given the parameters. And here we are considering the plausibility of parameter values under the posterior distribution. So essentially what we do here is you try to find what is the corresponding location of this null value under the reference distribution. So you find its coordinate in the reference distribution. And based on how far is this location from the origin of the standard Gaussian, you have an idea how likely you observe this value under the posterior distribution. And the quantile of the reference, the quantile under the reference distribution, again, is just the quantile of a based on the distance, it's just a chi-square distribution. And the nice thing about using the OT map is the inverse map can also be conveniently computed. As the inverse map essentially is just the conjugate, the gradient of the conjugate function to the optimal potential function. So you can just solve this convex program, and you will obtain the inverse of the inverse at a specific point. And you can just use any kind of gradient algorithm, gradient descent algorithms to solve this convex program. And besides the p-values, this inverse function can also give you a way to say, if I have multiple draws from this posterior distribution, I can also use the inverse map to rank them. So essentially, here you find, I happen to have 10 draws from this banana distribution, and I map them back to the reference distribution using the reverse map, and based on how close they are to the origin of the reference distribution, the closer they are to the origin, I will assign a smaller rank to these values. And now I will talk about I would say the most technical part of this talk, how you want to find the OT map when you have both discrete and continuous variables. And this happens all the time in Bayesian inference. We use hierarchical models all the time, and you always have the discrete latent variables. So the bad news here, when you have both discrete and continuous variables, your target distribution is no longer absolute continuous, and you lose some of the nice property that your continuous case will have. Your optimal transport map will not be invertible. And another consequence is since the pre-specified transport class will also not be invertible, you are not looking at the gradient of strongly convex function, but just gradient of convex functions. So the T star and the T are both not invertible, and there's no tractable form for the transformed properties. To do the change of variables, you need to be able to compute the inverse map. And because there's no inverse map, you also fail to rewrite this KL loss function. There's no equivalence between these two loss function now. So our solutions follows in 3 steps. So first, we need to define a new Monte problem. So we need to rewrite the L2 loss transport class. And the second step is we derive a new characterization of the optimal potential function and the optimal transport map under the new Monte problem. And the third step is we provide new ways to implement the KL loss to find this the new U star and the T star. And the first 2 steps are actually also novel in terms of OT theory. Usually for the OT theory, people focus on, say, if I transport a continuous to a continuous, or if I transport continuous to discrete or discrete to continuous, which we refer as the semi-discrete case, but not really any results on, say, if I want to transform a continuous to a mixed distribution. So our first step here is I need to redefine the Monte problem. So before, I only have the L2 distance between my reference distribution and the transform distribution. Now I want to separate the transport cost on the discrete part. So I partitioned my reference distribution into 2 parts. I have Z1 and Z2, where the Z1 will, I try to minimize the Z1 and the discrete component, and I also try to minimize the Z2 and the continuous components costs. And we introduce a scaling parameter kappa here to control the relative impact of discrete component in the overall cost. So in most cases, you can just simply set kappa to be 1 to have an equal contribution. But we will show later in some of the latent variable cases, the cardinality of your discrete components can grow exponentially with respect to your number of observations or your number of covariates. And in this case, you want to avoid the discrete component cost to dominate the continuous cost. And you will set K to be some scaling parameter depending on the sample size. And the second part, the second step is given the new Monte problem, we will have a new characterization of the optimal potential function and the optimal transport function. The takeaway message here is we need to treat the discrete and the continuous components separately. So before, we have partitioned the reference distribution into Z1 and Z2, and here we do the same thing for the transport map. The T1, we partition into T1 and the T2. And the T1 is essentially taking care of matching the discrete components given Z2. And the T2 is taking care of matching the continuous component. It's kind of like a sampling, it's kind of like a clustering problem. If I give you the membership, that's why it's actually T2. If I tell you the membership in the discrete component, you will know the distribution of each cluster. And the first step is if I tell you the distribution of each cluster, you will know which label to assign to the discrete component. And the difference between this algorithm and the clustering algorithm is the loss function here is convex. So you will be able to find a global global optimal solution in this case. And the third step is to how to implement the KL loss, since we no longer have an invertible map. So one observation you probably noticed from the previous step is the second part of the map, which I'm given the latent variable, and I try to map the second part of reference distribution to my continuous component. This part, essentially I'm mapping continuous to continuous. So this part of the map is still invertible, and we want to take advantage of that. So we will introduce an intermediate transport map, T tilde, that's only acting on the second part, only acting on the second part of the reference distribution, and then map it to my continuous component of theta. So the T tilde here is still invertible, and that will give me an advantage that I can still rewrite the KL loss for this part. And this kind of like a similar representation of the loss function we had earlier, except now I have another part of loss that is given given your Z2, where Z2 lies in the reference distribution. I will need to solve a maximization program to find its membership in the discrete component. And the one challenge I mentioned, I briefly mentioned earlier, say for say for example, for Bayesian latent variable models, a lot of times the cardinality of your discrete components can grow exponentially with your number of observations or your number of covariates. So if we think about the simplest case where you have a mixture of Gaussians with k components, so the membership of each observations has k possibilities. So for each observation, it can belong to one of the k clusters. So if my discrete component tau is trying to keep track of everyone's membership, so the memberships of n observations, these components will have k to the power of n combinations. And for my previous implementation, I need to estimate one OT map for every combination. So that will brings me to say I need to estimate k to the power of n of these convex functions. So we propose a mean field-like approximation for this specific case, where we break down this phi conditional on all of the observations into the sum over individual functions that only taking care of one observation at a time. So in this case, this will simplify the number of functions to estimate from k to the power of n to be say linear in n k. And another special design we considered in our paper is when you have a really large sample regime, the BVM theorem basically suggests that if your model is identifiable for a parametric model, the posterior distribution will be asymptotically normal. Then essentially, I'm trying to find the OT map that can push forward a standard Gaussian to another approximately Gaussian distribution. And in this case, I only need to find a linear affine class, trying to learn basically the location and the scale parameters of this approximate Gaussian distribution. And even with this simple transport class, this will give us an estimation error to be at the root n rate. And now I will show some simulation examples on how our method compared to other also transport map-based method. So one method is what we mentioned earlier, is the normalizing flow using the planar transformer, and another method is transport Monte Carlo by Liu Duan in 2021. So here, the first simulation example we consider is the mixture of Gaussian distribution. So the blue dots here are the exact samples from this mixture of Gaussians, and the orange ones are the approximated samples generated by different transport maps. So you wanted the orange dots to line well with the blue dots. And you can see here, the normalizing flow, for the normalizing flow, it captured all 10 clusters, but it also still struggles to say for certain clusters, its samples didn't align completely with the target distribution. And for transport Monte Carlo method, because this is not really designed to take care of the multimodal distribution, so it only identifies 4 modes. And for our method, as I mentioned earlier, we will use we design our U function as a maximum of k convex units. And in this case, even though the ground truth is 10, we set the k to be 32, so it's over parameterized. But I think it works really well for this example. And the second simulation is the logistic regression. So it's just a simplest setting where I have n binary responses, yi from 0 and 1, and their p-dimensional covariates. And the likelihood of the posterior of the coefficients is just proportional to the likelihood and the prior. So in the past, because of this complicated likelihood, it's actually not that straightforward to do conjugate sampling for the logistic regression models. And a lot of the time you still need to use, say, at least data augmentation to sample from this logistic posterior. So here we consider non-conjugate and non-informative prior, which is just a pretty flat normal distribution. And we generate our covariates from normal 0 sigma, where the sigma is this populist matrix to induce some correlation among different covariates. And we consider kind of a large sample setting where you have 1,000 observations, 1,000 observations with 10 covariates. So in this case, you could expect that the true posterior will be asymptotically normal. So we compare our method using just a regular construction of the U function, and also the method that we mentioned earlier, using only the linear affine transport class. And we also consider normalizing flow and the transport Monte Carlo. And in this case, because we cannot sample directly from the posterior, we treat the Gibbs posterior as the benchmark to compare. So we have report 2 kinds of results here. The first one is we want to compare the 95% intervals. And we include 2 types of intervals, the credible intervals and the predictive intervals. So one is the solid one is the credible intervals, and the dashed one is the predictive intervals. And for this plot, you observe that even because it's a kind of in the large sample regime, using a linear transform map, the blue ones, the results is already good enough. It's very similar to the green one, where we use a more complicated construction of the convex function class. And the normalizing flow, and we are still using the linear, even using the linear map, we are performing better than a normalizing flow. And the second plot is we're directly computing the standardized 2 Wasserstein distance between our posterior draws and the Gibbs posterior. And again, we have a similar conclusion that our sampler is closest to the Gibbs posterior, regardless of the correlation strength. And I think the more interesting application here or example here is we wanted to show how our credible, our 95% credible regions may help you to do data exploratory analysis in this case. So we consider a slightly different setting this time. So we consider a sparse setting where my beta is still with 10 coefficients. And I specifically set 5 of them to be 0 with a median correlation of 0.5. So the first example we consider here is I wanted to understand how each beta j, each coordinates compared to 0 for j from 1 to p, 1 to 10. So the first plot is the marginal density of the posterior of this beta 9 and the beta 10. And that's if you're not using shrinkage prior, this is how you usually say have an understanding whether these variables are significant or not. And in this plot, the first thing you will notice is both our posterior is at least the marginal density is very close to the Gibbs posterior. So this match our observations from the previous slide. And in this plot, if you only like the marginal density, you'll probably have the conclusion that both beta 9 and the beta 10 are likely to be significant variables. But since here I know the ground truth beta 10 should be 0, so the marginal view here will kind of overstate the evidence against beta 10 equals 0. And the second plot is if I try to understand the correlation, if I want to take into account that there might be correlation between different coefficients. So I construct my 95% credible region for this 10-dimensional distribution. I try to construct the 95% credible region for the entire beta. And then I project this credible region into the 2-dimensional views of beta 9 times beta 10. And then I found the smallest box that can contain this 95% credible region, which is the 95% simultaneous CIs. So in this case, you will see that the beta 10 equals 0 actually intersect with this 95% credible region. Or it also intersect with, of course, it also intersect with the 95% simultaneous CIs. So if you are trying to do exploratory analysis using these simultaneous credible intervals, you might find different evidence about, say, whether beta 10 should be 0 or not. And the second example for this simulation is we want to go back to the Bayesian p-value example. Say we just use a naive example. Say I want to understand how plausible is the the beta null equals just 0 vectors. So what I do here is I try to find what is this null vector corresponding location in the reference distribution. So I solve optimization program to find its original location in a standard 10-dimensional Gaussian is just these coordinates. And this will give me an L2 norm of 74.5. So if you quantify the distance of this dot to the origin, is 74.5. So this will give me an idea about this joint configuration beta null is extremely unlikely under the posterior distribution. So you can do it in 2 ways. So the first, you can say I want to compute the radius of the 95% credible region for a 10-dimensional standard Gaussian, which is just the square root of these chi-square quantiles. It should be around 4.3, which is significantly smaller than 74.5. Or another alternative is I can compute this Bayesian p-value is I feed this norm into the chi-square quantile. And this is because it's extremely unlikely. So in this case, it's smaller than the machine precision, 2 to the 10 minus 16. So either way, you will figure out this, at least this naive no values is extremely unlikely. So one thing we want to emphasize here is we are not trying to market this as a rigorous testing procedure, but we view it more as a nice way to do data visualizations and exploratory analysis. And it's easier for you to draw insights that can be helpful for you to, say, design a more rigorous testing procedure to verify these findings. And to sum up this talk, here we propose a novel approach to learn the optimal transform map T star from a reference distribution to your target distribution with an unknown normalizing constant. And we enjoy computational advantages such as it has a unique solution obtained by just solving an optimization program. And once you find such map, you will get almost exact independent draws from the target distribution at a very low cost. And we have a tailored characterizations for mixed variable case. And then you also enjoy inferential benefits that you can easily construct center outward ranks and quantiles for posterior summaries and exploratory analysis. And something we didn't go over in the talk is it is also the most parsimonious and interpretable map. So if you say, if I choose my mu to be my prior distribution, then once I learned this OT map, I also learned what is the transport distance from my prior to my posterior. And this will give me an idea about how much my belief have shifted after observed data, after I observed the data. And the good news is, if you are interested in the talk, the manuscript was out 2 weeks ago, and you can find more details by just scanning the QR code. And that wrap up my talk, so I'm ready to take more questions.